So yesterday we finished on the equilibrium constant, and now we just continue the same topic, that like how you can consider the application of equilibrium constant to the things related to any reaction. Okay. So by knowing the equilibrium constant, we came to know so many things. First, we can predict the extent of reaction on the basis of its magnitude. Means on the basis of our calculation or the numbers, we just can predict the extent of reaction. Means what is the extent, what is the speed of reaction, whether it is going slow, whether it is going fast. So if you want to say generalize this thing in one term, so you can say that by knowing this we can predict the rate of reaction, or how much reaction has processed, if it is near to finish, if it is near to the equilibrium state, or it is started. Okay, so we can find out the extent of reaction, that how much the reaction has finished, whether it is in forward direction or whether it is in reverse direction. Okay. Next, we can predict the direction of reaction. Direction of reaction is like when the reaction is moving from left to right, so that means that reaction is forward direction. And if reaction is moving from right to left, that is a reverse direction. Okay, so by knowing the equilibrium constants, we can find out the direction of reaction, that in which direction the reaction is going on. Next, calculate the equilibrium concentration. By knowing the equilibrium constants, we can calculate the equilibrium concentration of reactants and product at any point. Okay, so let's just elaborate all 3 points with how we can know this thing. So how you can predict the extent of reaction, that is the magnitude of equilibrium constant Kc and Kp is directly proportional to the concentration of the product and inversely proportional to the concentration of reactant. Means the magnitude of Kp and Kc, means if the magnitude of Kc is high, then it just tells us about the things related to the reaction. And if Kp is high or low, so we can just know about the extent of reaction. Okay, so the magnitude of equilibrium constant Kp and Kc is directly proportional to the concentration of product and inversely proportional to the concentration of reactant. Right? If the value of Kc is larger, means if we have the value of Kc is larger, then what, the reaction is proceed nearly to completion. If Kc is larger, it means reaction is about to finish, about to complete. And if Kc value is small, then the reaction process is rare. Okay. So as you can see this thing in a small figure, this arrow shows the direction, means the end shows the reactant side, and the point of the arrow shows the completion or the product side, right? So if the value of Kc is in minus, if we suppose this thing a number line, this is 0. If we go right, and this is the positive, we'll moving towards the positive. And if we go towards the left, it means we are going towards the negative. More negative is there, it means value of Kc will reduce. More positive will be there if this means that the value of Kc is high. Okay, so what happened when the value, when you just find out or calculate the numerical, and you will obtain that the value of Kc is less, or it's near to the minus line in the number line, or the value is in minus, so it means that the reaction process hardly at all. Okay, and if the value of positive is there, and that too very high, so you will see that the reaction proceeds to completion. Okay, and in at this stage the both reactants and products are present at equilibrium. Okay, so by knowing the value of Kc, we can predict the extent of reaction. Okay, next, predicting the direction of reaction. How you can predict the direction of reaction? First, the equilibrium constant help in prediction the direction in which a given reaction is will proceed at any stage. So for this purpose, we calculate the reaction quotient. We have to calculate the reaction quotient. Okay, it denotes with the QC with molar concentration. QC is reaction quotient and C is the molar concentration, because now we are talking about the molar concentration of reactants in product, how many moles combined together and how many formed, right? So QC is the reaction quotient. If the value of QC is larger than Kc, what happens? This means that reaction is moving in the reverse direction from product to reactant. If QC is high, the reaction is in reverse direction. If QC is less than Kc, the reaction will proceed in the direction of product. That means the forward direction. So by calculating the numerical or the or your whatever problem you have, so by calculating all the things present in a equation, we can calculate that if QC is high, it means the reversible direction will be there. If QC is less than Kc, it means the forward direction will be there. Okay, right? So how you can calculate QC? For example, the formula will be same like KC and KP we were calculating. We were calculating the KP by the formula, same formula. But the like now when we are here talking about the KC. Okay, so how you can find out the QC and KC? The formula will be same, means the reactant upon product. Okay, and the coefficient will raise to the power of the respective element. Okay, so for example, if I am performing an experiment and small a is the coefficient, means number of moles of capital A, small b are the moles of capital B, small c are the moles of capital C, and small d are the moles of capital B. So what we'll do QC is equal to product upon reactant, and these coefficients, stoichiometric coefficient, will raise to the power of their element. For example, this in big bracket we will put the elements or compounds whatever we have in the product side. So capital C to the power small c, capital D to the power of small d, upon divided by capital A to the power small a, capital B to the power of B. That is how we can calculate the QC. It's just similar to the KC. That's it. This how we can find out the molar concentration. That now we can find out the equation quotient of molar concentration. Now, how we can predict the direction? We know this thing that direction will be, we have done. If QC is greater than KC, what happened? The direction will be in reversible direction, and if QC is smaller than KC, the direction will be in forward direction. As you can see this thing in diagram. If QC is less, it means reactants are less and products are more. This means that the direction is in forward direction. Okay. When you will see the QC is equal to KC, it means no net reaction occur. Means the reaction is at equilibrium state, no reaction occur at this time. Whenever we found QC is equal to KC. And if you will see that the amount of product is less as compared to the product reactants, and the value of Kc is less and Qc is more, it means the reaction is moving in the left direction. It means that is reversible direction. I think this will be clear to you all. Okay, Qc more, net reaction is left. Kc more, it means the reaction is moving towards right. If both are equal, it means no net reaction occurs. Okay, so now how we can calculate the equilibrium concentration? The most important thing. So first, what we have to do, first we have to write the balanced chemical equation for the reaction. The first thing is you have to write a balanced chemical equation in which you just balance it with the number of moles. If balancing will be different or wrong, your entire solution will be wrong, because the coefficients, stoichiometric coefficients of number of mole will be raised to the power of that compound when you just calculate the Kc or Qc. Okay. Second, under the balanced chemical equation, make a table that lists for each of substances involved in the reaction. Now you just make a balanced table in which you just collect all the data, whatever is given in the question. First, the initial concentration. Initially, when we start the reaction, the concentration of product will be more, reactant will be more, and the concentration of product will be zero, because initially when we start the reaction we takes the only reactant. Okay, so that is why initial concentration will be different from molar, and it is different in reversible process. The initial concentration of we see in the backward direction. So what happened? The product concentration is more and reactant will be less. Okay, so we just have to find take initial concentration. Second, the change in concentration on going on to equilibrium. When the reactions start, so what happened? It's just going towards the equilibrium to attain the equilibrium, and at one point equilibrium gets established there. So we have to find out the change in concentration, means final concentration, equilibrium concentration minus this initial concentration. Next, just you will get the equilibrium concentration, and you can calculate how. Next, you have to substitute the equilibrium concentration into the equilibrium equation for the reaction and solve for X. Whenever we start anything, we don't know that whatever the exact amount of that substance is, or whatever we have to find out. So we just substitute in place of that is S. For example, we just assume things in maths also, that let this will be X. Before starting the experiment, we just measure or give a specific entity to that unit. So that means that this here will be X. So now we have to solve for X. We have to find out the value of X. So if you to solve a quadratic equation, choose the mathematical solution that makes chemical sense. Now we have to calculate things through mathematical sense. Calculate the equilibrium concentration from calculate the value of X. And whenever you get the value of X, now you can find out the equilibrium concentration by substituting that value of X in the equation. Now check the result by substituting them into equilibrium equation. Now whenever you get the value of X and everything, you have to substitute all the things, all your result into the equilibrium equation, and you will get your answer, right? So let us do one example of both the things. For example, now if you have to calculate the QC, how you can calculate? So this there is a problem. The value of Kc of a reaction. Value of Kc is given. Reaction is 2A gives B plus C. Okay, this 2A is a reactant and BC is product. So 2A gives B and C is 2 into 10 to the power minus 3. So Kc for the reaction is this, the value of Kc is this. So at a given time, the composition of reaction mixture is A is equal to B is equal to C, that will be 3 into 10 to the power minus 4 M. Means the molar concentration for all reactant and product is same. So in which the direction will be processed. Now for that we have to calculate the value of QC. So QC is equal to product upon reactant. We know this thing that, and the coefficient, their coefficient, stoichiometric coefficient will be raised to the power of that element. So BC is the product upon AC, A square. Okay. So we know this thing that A is equal to B is equal to C. All the molar concentrations of all the elements are same. So in QC, we just substitute this 3 into 10 per minus 4 in place of your elements. So QC is equal to 3 into 10 per minus 4 bracket 3 into 10 per minus 4. You can write it as square also. 3 into 10 per minus 4 square, because both are same, upon 3 into 10 per minus 4 square, right? Because already we know this thing that there is a one square, stoichiometric coefficient square, and we'll find our answer A. So we know this thing that 2 into 10 power minus 3 was given. The more Kc value of Kc was 2 into 10 power minus 3, and now we obtain 1 here. So Q is greater than Kc, because 1 is greater than that minus 3, 2 into 10 power minus 3. Okay, so that is why the reaction will proceed in the reversible direction. Now we'll just do one more question, or to find the value of Kc and everything. Okay, or we can predict the like equilibrium coefficients or constant we can find out. So what? There is a problem. 13.8 gram of N2O2 was placed in 1 liter reaction vessel at 400 Kelvin and allowed to attain at equilibrium. So this is your reaction. N2O4 is a reactant and which makes 2 moles of NO2, right? So there are so many things given about this reaction. First is the total pressure of the equilibrium was found in 19.15 bar. This is the total pressure at equilibrium, okay, on the gases. Calculate the Kc, Kp and partial pressure of the equilibrium. Here we have to calculate the Kc along with Kp and the partial pressure exerted by each gas at equilibrium state. So we know this thing that if we talk about gas, so PV is equal to nRT. Ideal gas equation will be there. Okay. Here we have pressure, temperature, volume, everything. So let's just substitute these things into this equation. So PV is equal to nRT is ideal gas equation. We know this thing. Volume is 1 liter given. Molar mass of N2O4 is 92 grams. And if you want to find out the number of moles, so you have to uh, divide the given mass upon molar mass. That is, given mass is 13.8 grams. This is already given in your question. Divided by 92 grams, that will be 0.5. So as value of small n is 0.15. Gas constant R red. This is Redberg constant, and we know this thing that we know the value of capital R because this is constant for ideal gas equation. That is 0.083 bar liter mole inverse and Kelvin inverse. Temperature is already given here, 400 Kelvin. So we just substitute all the entities into this PV is equal to nRT formula. So we'll get the pressure 4.98 bar here. Okay. Next, if we talk about the initial pressure and equilibrium pressure, so how we have to calculate the partial pressure. So initial pressure is 4.98. Right now we have calculated, and initial pressure of NO2 is 0. Why? Because initially we just have only reactant. N2O4 was there, no NO2 was there. So initial pressure of NO2 will be 0. At equilibrium, 4.98 minus X bar. X is the partial pressure we are just substituting here. And 2X pressure. X is the means assumption. X is assumed pressure. So if 2 moles of NO2 will be there, so 2x means double pressure was there. So 2x bar at equilibrium pressure. Now, if you want to find out the P total means partial pressure or total pressure exerted by the gases is equal to pressure of N2O2 plus pressure of NO2. So what we have to do, we know this thing that 9.15 was the total pressure exerted by the gas. 4.98 I have just calculated minus X is the assumed pressure plus 2x is assumed pressure for NO2. So if you just calculate it, you will get the value of X that will be 4.17 bar. Okay. Now, if you want to find out the partial pressure exerted by each gas in that chamber, is you can calculate it by this. You just substitute the value of X into the previous formula. What was that? PNO2O4 4.98 minus 4.17. As we know this thing that we just have assumed this 4.98 as the pressure exerted by N2O4. Okay. Next, PNO2 is 2x. We know this thing that we just assume the pressure exerted by NO2. 2 moles of NO2 is 2x. So just substitute the value of x is in this formula and you will get the PNO2O4 was 0.81 bar. The P partial pressure exerted by NO2 gas is 18.34 bar. So now we can calculate the Kp. Okay, so Kp will be like product upon reactant. So product, we know this thing that we know pressure is twice because 2 moles are there. So PNO2 is square upon N2O4. So that will be 8.34 square upon 0.81 is equal to 85.87. The value of Kp is 85.87. And the value of K, now if we have the value of Kp, we have R, we have T, now we can calculate the Kc. So by substituting the value of Kp, R and T in the formula of this Kp is equal to Kc RT delta N. So that is Kp is 85.87, Kc is Kc because we have to calculate it. R is constant 0.083 and 400 Kelvin temperature is there. Now, if we talk about the delta N is the number of moles, change in number of moles. So we can see that 1 mole of N2O4 gives 2 moles of NO2. If you want to find out the change, you have to minus the number of moles of product from the reactant. So means 2 minus 1, 2 minus 1 is equal to 1. So change in delta n will be 1. Okay. So we just put 1 here, we calculate it and we get our answer that will be 2.6 or 2.586. So that is the value of Kc. That is how we can calculate the partial pressure exerted by the gas in a chamber, the Kb and Kc. Right?